SwayamPrabha. Digital India. Educated India.
So you can think of this also. So x can be the same variable, you're doing a random walk. So this is what is the first step, second step, so on and so forth. And then this variable y is how far the person has gone away after n steps. So n is like time, right? So let's come back to this. This says that, and usually we'll assume that the random drunken guy will not, his mean will be 0. He always, drunk will always come back, right? So the mean is 0, but the variance grows as n times this thing. So what it says is that always a drunk will come back to the starting point, but if you can ask how far, the average, I mean sigma tells you it goes away like root n. So the distance will be some constant times square root of time. That's what this tells you. So this is where the additive property which I mentioned is very important. So this same thing has so many different applications, like the experiment, the the random walk, so on and so forth. The same ideas. And so the variance is defined because of this property, that combination. So we're now going to do a physics problem. So now the setup is the following. I have a box. Okay, this is a 3D box, but I have a 2D blackboard, so a square is my approximation to a box. It has volume V. Okay, and there are n particles. So it could be some gas, oxygen, nitrogen. Okay, it's not air. Air is a mixture. I can do that also, but for today, this is my setup. Okay, and I want to answer one question. So the whole idea is that there are a bunch of particles, they are moving around, there are collisions with the walls, collisions among themselves, etc., etc. A lot of things going on. Okay, so we could focus on one particle, okay, and try to track it and ask what is the velocity. There's a problem with that, because every time there's a collision, its velocity is changing, right? So it's not going to be constant in time.
So here you are asking the mean velocity or the most probable velocity or the root mean.
I'm more ambitious than that. I'm going to ask what is the probability distribution and give you the answer. Okay, it's asking mean, that's just one number. We'll get the whole distribution. Okay, so velocity means what? I have Vx, Vy and Vz. Okay, so these are 3 random variables for me because it's changing. So if you are looking at, there's something called an average collision time. Okay, and so if I'm looking at time scales where multiple collisions happen, so each time I sample, I will get a different value. So the idea is that, so we model the probabilities of So I'll write some capital P. And velocity, so the x velocity, y velocity all can take values from minus infinity to plus infinity, each one of them. So this will be a true density times okay, yeah. Coming attractions. Yeah, I need few more things to describe this gas, and yeah, absolutely right. We expect them to be independent. Since you said it, maybe I will write that. Okay, so okay, so then we will write something like this. So here I hope you understand what I mean by this is that Vx lies between Vx and Vx plus delta Vx, Vy lies between Vy and Vy plus delta x. So that gives you the probability. Okay, so somebody says that I don't know, capital Vx. Okay, something like this. They are all independent of each other. But I would just want to discuss some ideas. Okay, so the point here is that we will assume some properties, and we'll assume properties is that the system first is that system is in thermal equilibrium. So what does it mean that the system is in thermal equilibrium? One way of saying it is that this probability doesn't change with time. But I'll make a slightly different statement, is that, so I started off by saying what is the velocity of a tagged particle, but no particle is special. Okay, so I can do, so if I'm doing averages, there are two kinds of averages. First one is you pick a particle and keep following it and checking its velocities. System is no, it's jolly well doing whatever it's doing. There are collisions happening, etc. Nothing. We can do a time average. That means you pick a particle and follow it, and suppose you want to get, somebody said mean velocity, find its velocity with time and average. So you do this. But we can also do something like ensemble average. I have to explain the word. Ensemble means collection. So what you do is you pick n particles, not same, at a given point, a fixed time you pick, but you pick n distinct particles and get there. You write the same formula, but except here this was the time index, there it's particle index. I'll use the same formula. Okay. So the idea of equilibrium, thermal equilibrium, is that these two averages are the same, and more stronger is that the probabilities are the same. Okay. So first thing is that the thing is that so the system is in thermal equilibrium means if you compute this average, it's not going to depend on time. It's going to be constant, number one, and time average is also equal to ensemble average. So no ergodicity, it doesn't matter where you do the measurement, etc. Of course, we are assuming the system is big enough. Okay, so So this is the first property. The second, I'll assume two properties and we'll come back to all these things. Okay, and two other properties. One is called homogeneity, which is the same as saying that there is no special point. I know you'll say, oh, there are walls, points close to the wall, but we're assuming that the system is so big that we can neglect those effects. So generic points, there's no special point in this thing. Okay. The third assumption is isotropy, which means no preferred direction. Okay, so we are interested in the velocity distributions, but the most general thing to write would not have been just this. We should have written something like this. Maybe location dependence. This is the most general thing we could have written. But homogeneity will tell you that there's no special point. So that means it has to be independent of x, y, and z. So this is homogeneity. Isotropy tells you no preferred direction, etc. And in some sense that will tell you that this little p of Vx okay. I wrote something somewhere else, right? I wrote PVx. I wrote as if x, y, and z have different. It's stronger than Vx, Vy, Vz being independent of each other. It says whatever is the Vx distribution, it should be the same as Vy and Vz. They should be identical distributions. So this is what we will get from isotropy. It has to be product of these guys. Independent tells you that it won't tell you that the probability is, I'm using isotropy to, yeah, independence will tell you that, but it won't tell you that what I'm writing is the same function. I'm writing the same function. There I wrote three functions. Yeah. So this is what we get. Okay, but isotropy is something, it gives something stronger. Okay. It also says that it shouldn't depend, it should depend on some, but V is a vector, so it should depend only on its magnitude, actually magnitude square. So this should be some function of V square, because that is the only combination which has no, otherwise if you give me a velocity, the velocity has a direction. Non-zero velocity, it has a direction. So what it says that it has to be only depend on the combination V square. So even though here I wrote capital P of Vx, Vy, Vz, it can only depend on the combination Vx square plus Vy square plus Vz square. Okay, so we're getting two different things, and these all have to agree. And now the question is, what can the answer be? We're going to work it out. Okay, and we'll get something very nice. Okay. So we get something. So what? I'll use the same notation P of V square, but that should be, what is a P such that this is what we want to answer. Okay. So anybody has ideas? How should we do this? Okay. So what we will do is, what is v square? It's a function of vx square plus vy square plus vz square, right? That's what it is. And so what I can do is I can vary, I can think of vy and vz as constant, and just take derivative with respect to vx. Yeah, it's called partial derivative. Yeah, but again, some people know multivariable calculus, some people don't. Okay, so what I'm going to do is take derivative with respect to vx, keeping so those of you who know that, it's just the partial derivative of this thing. Okay, so now left hand side, and I'll just do a small trick which is not necessary. I will take log of this. I'll take derivative of log of log. I'll use log, but that's natural logarithm. Okay, in physics we never do base 10. We always have base e. Okay, so notation is log equal to ln in my lectures. Okay, so we have to use the Leibniz rule, the chain rule. This is a function of v square. So this is 1 by pv I hope you understand. I mean, you think of v square as a variable. Okay, that's LHS. RHS has the following property, that its log becomes additive. So Vy and Vz are constants with respect to Vy, so I can throw them out. Yeah.
Sir, I didn't really understand why we are taking the derivative and why we are taking log of v.
Oh, that is just a trick. You don't have to. Yeah, it will make my life easier. Yeah, on the one reason is that these guys will drop out. That's actually the main calculational reason. Yeah, so the thing is that to define v, speed, involves a square root. Square root is not a nice function. It's not analytic. It's a mathematical requirement. Okay. It's a nice question. So that would be now d by dvx these two have to be equal. Okay, but can someone tell me what is d by dvx of v square? Two vx. Okay, because vy square, vz square are constant. You forget them, so it's just taking derivative of vx square, which is 2vx. So now we are set. So we get these two LHS should be equal to RHS. Oops, sorry. So I'll equate them, and what I will do here is pull this as a Vx dependence here. I'll bring it to this side. Okay, so I'll get Okay, so look at the left hand side. Now, left hand side depends only on the combination v square. So there is Vy square and Vz square dependence on this. What about here? Right hand side has no dependence on Vy or Vz. So now comes the puzzle, how can these two be equal to each other? When can a function of x, of one variable Vx, be equal to a function of three variables? Only the other two variables are common, but no, it has, that combination is coming. It's through this combination v square. So you can refine your answer now. So everything, so the only way it's possible is if this is equal to some constant. Both are equal to constant. Okay, and let me call that constant minus alpha. Can you people work out what it implies? So that gives you some value for p. It also gives you for little p. Can someone work it out? Both. This is the easier one. It says d by d log of something. So it implies log of pv square equal to minus alpha. I can integrate once. Okay? And these two are compatible with each other. So let's look at P of Vx. Have we seen this distribution anywhere? It says Vx, Vy, Vz are normal. What is the mean? No. No. If there was a mean, non-zero mean, that means there's a preferred direction. So only answer is 0. It's x minus mu, right? This mu is 0. So it's a normal with mean 0 and alpha is some standard deviation. Alpha is something which gives the standard deviation. Yeah, it's all peak centered at 0. The peak is at 0. So the mean is 0. So yet another reason to, it says that the velocity distribution in a gas which is located in something is proportional to alpha. It turns out that this alpha can be is determined in terms of the properties of the gas. In fact, the alpha will be this is not obvious. Okay, so we need something. So it says that alpha will be m is the mass of the particle, Kb is something called the Boltzmann constant, and T is the temperature of the gas. So if you give me the gas, Kb is a constant, mass is also a constant. So the standard deviation, okay, so the variance of the gas is, so variance of the gas has physical meaning. It's proportional, is a measure of the temperature of the gas. So we get something very beautiful. Variance, which we define fancy mathematics and all, actually has physical meaning. It's the temperature of the gas. Up to factors. Okay. So this distribution properly normalized is called the Maxwell-Boltzmann distribution, velocity distribution. Okay. I'll repeat. Okay. So it's normal in each variable Vx, Vy, Vz. Because there are three random variables, the x values, y and the z. They are independent random variables, each of them with mean 0 and variance, which is I guess kb square root, sorry, kbt upon m is the variance. Yeah, somebody asked a question when somebody had a question. So in this example, the variance is a measure of the temperature. M is the mass of the particle. Okay, so you can see this is like pure thought. So this is the spirit of what Balki says, what can the answer be? I have 16 minutes, so I can actually do the other one also. It's actually an easier one. It's the same question, we'll ask a different question. So we have seen that the physical inputs were, system being in thermal equilibrium. Second was that homogeneity and isotropy. If you put all these things in, there's only one answer, which is this. Integrated once. So this d by dv square of log pv equal to that constant which I called minus alpha. So integrate once, it's alpha v square. Absolutely. Okay. So are there any questions? Oh yeah. So then if it were positive, then it's it's not normalizable. Its integral is infinity. It can't be a probability. Can't be a probability density. So yeah, so the minus sign is put in because I want a probability density. Nice question. Of course, in physics, we have a different way of deriving the Maxwell-Boltzmann distribution. This is not how we would derive it. We have physical ideas, we do some calculations, and we get the same answer. Okay. So the second one is the same setup. Okay. What I want to ask is I'll pick a small volume. I just drew a cube inside it with little v. Okay. And my question is, can I ask how many particles, so it's moving through this thing. So if I ask how many particles are located inside this volume, it will be a function of time, right? So I want to model the number of particles okay. So I can again do time average. I can pick a particular volume and keep counting the number of particles. I'll get some random number of variables. Some number I'll get. One time I will see 2, after some time 3, maybe 5, 10, it will keep fluctuating. So I want to ask what is the probability. So this number can be take all sorts of values, and we would like to ask, we have already done this. Balki has done this. He's done this. Very nice, very nice. No, but still, let's go with the spirit of it helps me. Okay. So, but did he do the limit? So this you will model with, what is the model? You got a binomial distribution. Yeah, okay. So let's write that. So we want to ask what is the probability of finding m particles in the gas. Okay, so so that should be where little p is the probability of finding inside the thing. Okay. By the way, this is not going to be my punchline. That's the point. This is not my punchline. This is just the starting point. First thing is, what is p? What is little p? Yeah. So the guess is small. Correct? So we have this thing, but we want to now, what we want to do is we want to take the thermodynamic limit. And what is the thermodynamic limit? Thermodynamic limit is to take the number of particles to infinity, take V to infinity, that's the idea, that the box is so large, numbers are large, but you want to keep n over V, which is the number density rho, is constant. Okay. So let's now ask, what does that mean? So what is the average number of particles in this, inside the volume? What is mu? Okay. So now let's look at this limit. N goes to infinity, V goes to infinity, but n upon V is rho. Okay. What does that make mu? Rho times rho V. So we can see in this limit, okay, mu becomes rho V. A little bit of thought will show you this was exactly the limit that gave Poisson. Here it's a physics statement that we are taking this, but you can see taking V to infinity is effectively as if we are taking P to 0. So it's a very physical input, and the answer is Poisson. Since I have 10 minutes, we will work it out. We will show how to get that. I didn't do that. So you understand, my punchline is different. This is the easy part. This is the fun part. Okay. So because that's really the setup. I mean, usually if you have, you will have Avogadro number of particles, n being, 10 power 23. That's truly large. So pretty good approximation that n goes to infinity. But when you want to double your system, you don't want to change characteristics of the system, and that tells you keep the number density constant, don't mess up things. Okay. So let's do the computation. Okay. So what is it? We want to take this limit. So what is it we have to do? So let's do that. So what is okay, so I will use the same thing which I wrote earlier, but hopefully you see that it's the same as taking this limit. I'm doing the thermodynamic limit. I don't want to keep bringing various things. So let's do that. Looks like my phone. This is what I have. Okay, so m is supposed to be some finite number, but capital N is going to infinity, and you can see that n into p, that combination is exactly, which becomes lambda, and lambda for our problem is rho v. Okay, so we get approximately okay. Now we still have to take this limit, but this m doesn't matter, but really this n is going to infinity, but p is going to 0. Okay, so I can rewrite this as limit n going to infinity, so n minus m and n are approximately the same. Hopefully you know this limit. What is this limit? It's e power minus lambda. So it says that you don't, it's best described by a Poisson rather than just binomial. Okay, so this again where a mathematical limit and a physical limit agree. Okay, so here are two examples where, you know, in some sense pure thought, and we are trying to model stuff, we get the answers. Okay, so I think I'm done here, and the floor is open for questions. I didn't use Stirling. I didn't need Stirling's formula. I just said that n is much larger than m, so I approximated this by n power m. That's all. I mean I could use Stirling's formula. I don't need Stirling's formula for this. Yeah, it will give, but it's like hammer for cracking a peanut or a groundnut. I don't need Stirling's formula. Okay, so one more thing which I also wanted to highlight this, that there are no compartments. There's not compartment called physics, mathematics, chemistry. They're all part of science, and maths is the language to write rigorous statements, and science is not about writing phrases in English. It's about concrete calculations. So we cannot say that everything was known, for instance, in the past because some word exists in the past. That's not correct, because today modern science is all about calculations and giving concrete numbers. I mean, it's amazing that a small thing like a GPS, which is now there in every phone, that requires, you know, not Newtonian mechanics, but it needs corrections from special theory of relativity. Okay, so the precisions we have reached in modern science is just amazing. So finding something, saying that it appeared in the past doesn't make sense, because the past we didn't know so many things, and we have evolved, and we are able to make precise statements. We are able to measure time to, you know, huge precision. We are able to measure length to various precision, so on and so forth. Okay. And so it's important to appreciate that the whole science is one big thing. It's not, I mean, there are interconnections. Okay, the kind of things I do, for instance, you can model, you know, in chemistry you will learn about reaction rates, etc. But you can model that as a gas of the variety which I just showed you. And so we get some properties of it from physics, which actually lead to, you know, you learn formulae called reaction rates, some ratios, activities, various terms are used, but those all follow from some very simple underlying principles, and of the variety which we saw.